Hi, I'm Bernie, and in the second NXSYS instruction video, I'm going to explain some very basic features of New York subway and similar signaling, some further basic features of NXSYS, finally, some more advanced features of New York subway interlocking control that you can explore with NXSYS and its applied interlockings. Although all of this relay-based signaling is technologically obsolete and rapidly being replaced by computer and communications-based train control, or CBTC, the basic principle of rapid transit safety they implement will never be irrelevant as long as trains have mass, momentum, and passengers and run below and above city streets. Let's start with the basics. New York subway trains are currently detected electrically as their axles connect the two running rails, i.e., not the third rail, allowing current to flow between them. In order for this to be useful, every track must be divided into sections, also called blocks or track circuits. The length of these vary between many hundreds of feet and few, depending upon what train speeds are expected or even possible, and how far the designers wanted to keep the trains apart. Because, once installed, the length of these blocks cannot be changed, this venerable technique is called fixed block signaling. Blocks or track circuits are separated by insulated joints, or IJs, in the rails, which generally look like this. A wedge of non-conducting material separates one track circuit from the next. Signals are located at IJs exclusively and acquire their station numbers from them. In NXSYS, insulated joints are these little breaks here with the same numbers as the signals next to them. These signals are automatic signals, that is, they are not controlled by the interlocking, but only by train motion. Although we certainly can create trains in NXSYS, as we saw in the first video, it's usually easier to test signals and interlockings to drop axles onto the tracks just by clicking on a section. The red dots, as in the real interlocking, indicate that the section is now occupied, and as you see, the signal at its entrance has turned to red. If I remove the axle or train, whatever it is, the signal returns to green. Notice that if I put an axle here occupying this block, all three of these signals are red. That's because the signal's control lengths overlap. If I put a train or axle here, this signal does not turn red. Its control length is from here to there. This signal protects the region from here to here, or more precisely, the region from here to here, because when there is a train or axle here, the train stop does not go up. But in any further block, the train stop does go up. What is a train stop? A train stop is a mechanical arm, as you can see here in this Wikipedia picture, north of 125th Street on the Broadway IRT, that when raised, because the signal is red, will engage a valve on a train and stop the train forcibly. Of course, it will not stop instantly, but only in a few hundred feet, because trains have momentum. This is Myrtle Avenue interlocking. Myrtle Avenue and Broadway, Brooklyn, is a real place on the BMT. Here's a picture of it I borrowed from a blogger. Suppose a train had just come from the express track to the local track and gone away, and switch 187 here is thrown like this. That's not a problem. The interlocking can put it any way it wants, right? Well, suppose there were a train here that were moving along at high speed, and although by the time it got here to signal 188, which I've shown full signal as 200, it would be stopped before hitting this switch, but that's not exactly so, because if the train is really moving at speed and has momentum, even if it were stopped here, it would still go for a couple of hundred feet, because trains do not stop instantly, and derail at the switch and conceivably fall over the elevated trestle and go down into the street. So that's not acceptable. So what does the interlocking do, or how is it designed to prevent that? Well, the answer is having approach signals, like 202 over here. It says 245, which is a station number. You can't see the number 202, which is written on the side, the BMT, but that doesn't matter. So if a train were to move along here, it would be stopped at this signal, and it would be slow enough not to derail by the time it hit this switch. Suppose switch 187 were normal, or not thrown, as is the usual terminology, and signal 202 were clear, meaning trains could pass it. In fact, its control length extends all the way to over here, which you can prove by dropping an axle here, and the signal becomes red. Something else has happened which is very interesting. Switch 187 is now locked. Do you see the red light? That means that we cannot move it by using the auxiliary keys or even by requesting routes. If I try to initiate at 184, expecting a train to go from the express to the local track, the interlocking complains. This flashing means that 187 is locked, and it's not just locked in some odd way, but locked by signal 202. That's why signal 202 is flashing. And if I cancel 202, now it is no longer locked, and the exits appear, and I can create a route from 184 to 170. And now you see it says to diverge. Suppose the express train has come and gone and taken the switch and gone to the local track and left, gone all the way to Manhattan, and we want to set up for a new train coming on the local track towards Manhattan and clear signal 202. Well, we can't call for signal 202 because the switch 187 is reverse, which is the correct word for thrown. But it turns out that it's not locked, and the interlocking knows that if we call for signal 202, switch 187 must be thrown normal. So, if we call for 202, look at that. The switch moves and 202 is clear, and it will not clear if it cannot be moved normal. So if we cancel 202, and we'll move 187 back again to reverse, and we'll ask the auxiliary key to hold it reverse by double-clicking on the letter R, and now we try to call for 202. As we can see, the interlocking will not even let us do so. If we unlock by clicking once, and we call for 202, now the switch moves normal, and 202 is clear, and 187 is locked by 202. Coming from East New York, it's going to switch over to the express track to go toward Manhattan. It turns out, even though 202 is clear, we can set up a route from 202 to 164, which will move switch 195, and that will not bother signal 202, because signal 202 is not protecting the facing point switch. 200 is doing that, and 200 is red, and stop is up. So if we call for that route, the switch will move, and 202 will not even notice. Now, suppose that train has come and gone, and 195 is left reversed, and I now call for 202. 202 does clear, except now it is cleared over the facing point switch, and its control length extends all the way to here. See, if we drop an axle there, it turns red. So a train in any of these sections will turn it red. Now let's suppose that that train on the local track from East New York has come and switched over to the express track and isn't completely gone, but stopped halfway in the station and still has a piece of it left in this section. Well, as we know, this is in the control length of 202. So if we called for 202, we can call for it, but it will not clear because its control length is occupied. But let's say we want to set up for the next train, which is a local. We want to stay on the local track. Well, that's easy enough. We can call for 202, we can call for 200 and set up a route all the way from here to here and do it in one step or two, makes no difference. And that route is all set up. Now, let's say we change our mind and say, I want that train to go to the express track too. So that's easy enough. So we cancel this part of the route and cancel this part of the route, and we'll use the entrance-exit system to set up from 200 to 184. 200. Wait a minute, what's going on? Why is switch 195 locked? And it will not let us do that. Well, it's locked, as we know, because of 202. But why? 202 isn't looking into a trailing point switch. What the system is telling us is that if we do move 195, and all of a sudden, this piece of a train will be thrown into the control length of 202, and 202 will be turned red. It is a basic rule of interlocking that no action other than the explicit canceling of a signal can make a signal turn red by itself, that is, without train motion. If the train were to move on, 195 is now free, and indeed I can set up that route from 200 to 164. This is called overlap lock, and is one of the more sophisticated locking features of this type of interlocking. I hope you've enjoyed this exploration of subway signaling and NXSYS features, and will download the application and documentation and experiment with them yourself. You can leave comments here. Thank you so much for watching.